Welcome, curious minds and sleepy thinkers. You found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked, the origin of the universe and the whisper of its fiery birth. But don't worry, we'll take it slow. This isn't a race through equations. It's more like floating through a galaxy of ideas with a cup of chamomile tea, letting the vastness wash over us gently. Our current scientific story, the one that whispers through the quiet halls of observatories and the thoughtful discussions of physicists, begins not with a sudden clap of thunder, but with an unimaginable surge, a gentle yet all-encompassing unfolding. It's a tale of an origin so profound, so fundamental, that it reweaves the very fabric of our understanding, challenging our intuitive notions of what empty space truly means and how existence itself could have begun. When we speak of this primordial moment, we often use the word explosion, a grand, almost cataclysmic burst that seems to set everything in motion. However, that word explosion carries with it a certain weight of our earthly experiences, doesn't it? It evokes images of fire, of debris, of fragments scattering outwards into an already existing void. But in truth, what unfolded was something far more subtle, far more encompassing, and infinitely more peculiar than any earthly event we could ever hope to truly visualize or even fully grasp. Imagine, if you will not, something bursting into space, but rather space itself, the very stage upon which all cosmic dramas are played out, the boundless expanse that defines our reality, beginning its grand sweeping expansion. Let us try for a moment to peel back the countless layers of time, venturing far beyond the reach of human memory, further than the oldest, most ancient mountains that pierce the sky, and deeper than the most abyssal, lightless oceans that cradle our planet. Picture, if your mind can stretch so far, a singular moment, or perhaps not even a moment in the linear ticking clock way that we typically understand time. In this unimaginable state, all the matter and all the energy that today dance across the observable universe, every shimmering star, every silent planet, every fleeting ripple of light, every complex thought that has ever been conceived, every dream that has ever been dreamt, every single breath that has ever been drawn, were not scattered thinly across billions upon billions of galaxies. Instead, they were concentrated, compressed, squeezed into a volume almost inconceivably tiny. Scientists, in their quiet precision, tell us it was smaller astonishingly than the head of a pin. A mere speck, yet holding within its infinitesimally small embrace the entire potential, the complete blueprint for every grand cosmic structure and every minute particle that has ever manifested or ever will manifest in the vast tapestry of existence. It is a concept that humbles even the grandest, most expansive imagination, a mere whisper of cosmic density that lies far, far beyond the comfortable boundaries of our everyday grasp. From this astonishingly compact and impossibly dense state, the cosmos, in an event we reverently refer to as the Big Bang, began its monumental journey. Once again, the word bang might conjure misleading images of loud sounds and sudden fury of a violent and chaotic release of confined forces. But this was a fundamentally different kind of unfolding. It was the very birth of space itself unfurling with an elegance and precision that belies its energetic origin. Like an infinitely intricate tapestry, slowly, deliberately being unrolled, think of it less as a spectacular firework exploding outwards into an already existing night sky, casting light upon pre-existing darkness. Instead, envision it more like a tiny, tightly wound spring, brimming with latent potential, which is suddenly gently released. And in its very act of unwinding, it creates the very space it expands into, pushing outwards, not into an external void, but generating the void as it goes. The stuff of the universe, the fundamental particles, the raw, undifferentiated ingredients of everything we now see, began to spread, to diffuse, to dilute, and crucially to cool. And as it did, the very fabric of space itself, stretched, pulled and billowed, expanding silently and imperceptibly in all directions, just as it continues to do even now in this very moment around us, carrying galaxies along its ever-stretching current. This primordial expansion, this initial cosmic breath, was not a violent, destructive act in the conventional sense, but rather a profound act of creation, of becoming, of the universe defining itself into existence. It was the instant when the cosmic clock began its relentless tick. When light first found enough room to travel freely across the nascent cosmos. When the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces began to differentiate themselves, each taking on its unique role from a previously unified, undifferentiated whole. In those earliest, most intensely hot and dense phases, the universe was not yet adorned with stars or galaxies, nor did it contain the complex stable atoms that form the basis of everything around us. There were only the most basic constituents, the raw building blocks of matter and energy existing in a state of unimaginable heat and density. As space expanded, it gently stretched the energy contained within it, causing it to cool. This cooling process was absolutely crucial, a cosmic exhalation that allowed energy to gracefully transform into matter. Following the profound whispers of Einstein's famous equations that link mass and energy, it was this cooling that allowed the elementary particles to form then the slightly more complex protons and neutrons, which would eventually come together to form the nuclei of the simplest atoms, hydrogen and helium. Picture, if you can, a primordial cosmic soup intensely hot and unbelievably turbulent, yet gradually inexorably thickening and cooling, allowing new emergent structures to gracefully coalesce from the undifferentiated stew. This gradual cooling, this gentle and continuous exhalation of the universe, laid the essential groundwork, paving the way for the intricate and astounding complexity we observe and experience in the cosmos today. The timeline that scientists cautiously whisper in their discussions, a delicate and ever-refining estimation, places this grand unfolding, this initial cosmic stretch approximately 15 billion years ago. A number so monumentally vast, so utterly immense, that it stretches the very bounds of our human comprehension, dwarfing any earthly timescale we can conceive. 15 billion years. What does that truly mean for us fleeting beings on a tiny blue planet? It means that for eons upon eons, stretching back into a time before, even the very concept of time could have truly solidified in its current form. This incredible silent process of expansion was already well underway. It means that the light from the most distant, most ancient corners of our observable universe has been faithfully traveling across the vast cosmic expanse for nearly that entire unimaginable span, carrying with it silent ancient tales of cosmic firsts, of the very first stars igniting their nuclear furnaces, of the majestic spiral and elliptical galaxies slowly forming in a swirling gravitational dance, and of the fundamental forces shaping the nascent cosmos. It is a journey of light, a silent, enduring testament to the relentless continuous expansion that began from that singular, impossibly concentrated point. Every photon reaching our telescopes is a messenger from the deep past, a tiny fragment of information from the universe's infancy, whispering stories across billions of light years, telling us about its incredible journey and the transformations it has witnessed. In those earliest, almost unfathomable moments of cosmic history, the universe was not the cold, dark, and sparsely populated expanse we largely perceive today. Instead, it was a swirling, incandescent maelstrom of raw, untamed energy, a turbulent, primordial sea of fundamental particles, constantly interacting, annihilating, and being reborn. There were no stars, yet no shining beacons of light to guide any hypothetical traveler. No grand swirling galaxies to define cosmic structures, and certainly no complex stable atoms that could form the basis of planets or life. Only the most basic fundamental constituents of matter and energy existed in a state of unimaginable, almost blinding heat and incredible crushing density. As space continued its relentless expansion, it simultaneously stretched the waves of energy contained within it, causing it to cool, just as stretching a rubber band can make it feel cooler to the touch. This cooling was not merely incidental, it was absolutely crucial for the universe's subsequent evolution. It allowed energy to transform into matter, a dance beautifully described by the renowned whispers of Einstein's famous equation, E=mv2. This cooling also allowed elementary particles, the quarks and leptons, to form, and then as temperatures continued to drop, these particles could combine to form slightly more stable structures, protons and neutrons, the very building blocks that would eventually come together to form the nuclei of the simplest atoms, hydrogen and helium. Picture a cosmic soup intensely hot and incredibly turbulent, yet gradually, almost imperceptibly thickening and cooling, allowing new, more organized structures to elegantly coalesce and emerge from the previously undifferentiated chaotic stew. This gradual cooling, this gentle and continuous exhalation of the universe, was the essential silent architect that paved the way for the emergence of all the astonishing complexity and diversity we observe in the cosmos today. The Big Bang, then, is not merely a simplistic theory of an initial sudden burst, a chaotic explosion from nothingness. Instead, it is a comprehensive, continuously refined narrative of the universe's grand evolution from that incredibly dense, intensely hot, and primordial state. It is a sweeping story that elegantly explains how the fundamental forces that intricately govern our reality, gravity, which pulls celestial bodies together, electromagnetism, which binds atoms and allows light to exist, and the strong and weak nuclear forces which operate within the heart of atomic nuclei, came to be, each differentiating itself and taking on its unique role. It explains how matter, the very substance of our being, formed from pure energy, a cosmic alchemy of profound significance. It details how the universe gradually cooled enough for light to finally travel freely across the nascent cosmos, giving rise to the cosmic microwave background radiation, an ancient faint echo of the Big Bang itself, which we can still detect today. And it describes how the first faint whispers of cosmic structure began to emerge from what was once an almost perfectly uniform, featureless expanse, setting the stage for the formation of stars, galaxies, and eventually the intricate tapestry of cosmic life. It is a story meticulously woven from the most delicate threads of mathematical elegance and the robust, undeniable evidence of astronomical observation, a tapestry constantly being refined, restitched, and expanded as our human understanding grows, driven by an insatiable curiosity. And so we gently begin our shared journey through the cosmos with this foundational yet profoundly beautiful understanding. A universe born not within a pre-existing void, but from the elegant, self-generating unfurling of its very own essence. A universe that, from a point almost impossibly small, smaller than the head of a pin, expanded and continues to expand into the magnificent, sprawling, and ever-unfolding expanse we now inhabit. It is a story that graciously invites us to shed our ingrained everyday assumptions about the fixed nature of space and the linear progression of time, and to embrace a deeper, more poetic, and ultimately more wondrous truth about the nature of existence itself. For in the gentle, pervasive hum of the cosmos, from the smallest fleeting quantum particle to the grandest, most majestic galaxy, echoes the enduring memory of that singular, astonishing beginning. We are all, in a most profound sense, children of that initial expansion, carrying within our very being the stardust and the primordial energy that first burst forth from that unimaginably tiny, infinitely pregnant point. And as we drift deeper and deeper into this profound understanding, we find not just a collection of scientific answers, but a pervasive, almost overwhelming sense of awe for the grand cosmic ballet that continues its silent, relentless performance all around us in every direction, every moment. This journey into the cosmic past is not just about facts, It is about finding a deeper connection to the vast, mysterious narrative of which we are all an intrinsic part, as we gently drift away from the colossal initial surge of the universe. Our cosmic journey continues, leading us into an era where the cosmos began to reveal more of its structured beauty, though still shrouded in profound mystery. For a very long time, as humans gazed up at the night sky, their understanding of the universe was surprisingly intimate, almost claustrophobic in its scope. Our ancestors, and indeed many of the greatest scientific minds for millennia, largely believed that the entire universe was contained within a single glorious swirling entity, our own Milky Way galaxy. Imagine, if you will, living within a magnificent cosmic island, believing it to be the only island in an otherwise boundless empty sea. The stars, those countless shimmering jewels scattered across the inky blackness, were thought to be just different points of light, varying only in their brightness or their position, all fixed within the celestial dome of our singular cosmic home. This perspective, while limiting in hindsight, made perfect sense given the tools and observations available. The night sky, to the naked eye, certainly appears to be a singular self-contained display, a vast glittering canopy overhead. Yet even within this confined cosmic view, certain astronomers, those with an especially keen eye and an even keener sense of curiosity, began to notice peculiar anomalies. They spotted faint, fuzzy patches of light, indistinct smudges that defied the clear, sharp points of the stars. These were not quite nebula, those swirling clouds of gas and dust within our own galaxy, nor were they clearly defined stars. They were something else, something subtly different. Some bold thinkers peering through the early rudimentary telescopes dared to postulate, to whisper a revolutionary idea. What if these fuzzy patches were not mere clouds within our own grand island of stars, but rather entirely separate island universes themselves? What if our Milky Way was not the solitary cosmic entity, but just one of many, perhaps countless such islands floating in a much vaster ocean of space? This idea was truly radical, a profound challenge to the long-held dogma of a singular enclosed universe. It was a notion that stretched the mind beyond its comfortable limits, inviting a dizzying sense of scale and possibility. However, for centuries, these whispers remained just that, unproven postulates, tantalizing hints and theoretical musings. There was no definitive proof, no observational certainty to confirm these island universes were truly external to our own. The fuzzy patches remained ambiguous, their true nature stubbornly resisting classification. The debate simmered, a quiet but persistent fire in the heart of astronomical inquiry, until the arrival of a pivotal moment in the 1920s. It was then that an American astronomer, a man named Edwin Hubble, stepped onto the cosmic stage, armed with a powerful new telescope and an even more powerful sense of meticulous observation. Hubble was a figure of quiet determination, a man whose patience matched the infinite expanse he sought to understand. He began to dedicate himself to studying one such enigmatic object, a prominent fuzzy patch that we now know as the Andromeda Galaxy. It glowed faintly in the night sky, a swirling enigma beckoning him closer. As Hubble painstakingly studied Andromeda in the year 1923, poring over photographic plates night after night, searching for clues within its distant glow, he stumbled upon a discovery that would forever alter humanity's perception of its place in the cosmos. Amidst the countless indistinguishable pinpricks of light that made up the distant nebula, he identified a particular kind of star, a Cepheid variable star. These are not just any stars. They are cosmic beacons pulsating with a rhythmic ebb and flow of brightness. Imagine them as tiny celestial lighthouses, blinking brighter and dimmer over the course of weeks, following a precise, almost musical rhythm. What made these stars so incredibly important, so invaluable to Hubble's quest, was a groundbreaking discovery made years earlier by another remarkable astronomer, Henrietta Swan Leavitt. She had proven with stunning precision that the period of a Cepheid variable's pulsation How regularly it brightened and dimmed was directly and intrinsically linked to its intrinsic luminosity, its true, absolute brightness. This was a monumental breakthrough, akin to finding a universal calibration for a set of light bulbs. If you knew how quickly a particular type of light bulb flickered, you could immediately know how truly bright it was, no matter how far away it might be. With this profound knowledge in hand, Hubble now possessed an unprecedented tool. By carefully measuring how regularly the Cepheid variable star in Andromeda brightened and dimmed, he could precisely calculate its true intrinsic luminosity. How bright that star should have been if you were standing right next to it. Then by comparing this calculated intrinsic brightness to how bright the star actually appeared from Earth, which, of course, was much, much dimmer due to its immense distance, he could, with remarkable mathematical precision, calculate exactly how far away it was. Think of it like this. Imagine you know that a certain candle always emits the same amount of light, no matter where it is. If you then see that candle from a distance, and it appears very dim, you immediately know it must be very far away. Conversely, if it appears bright, it must be close. The dimmer it is, the further away it must be. Cepheid variables provided Hubble with precisely this kind of universal, standard candle, an almost magical ruler with which he could measure the vast, previously unmeasurable distances of the universe. And what he found when he applied this cosmic ruler to that single blinking star in Andromeda was nothing short of astonishing. The star he was examining, that tiny rhythmic flicker of light, was so incredibly far away, so vastly distant, that it had to exist unequivocally outside of our own Milky Way galaxy. This was the definitive proof, the undeniable evidence, that the fuzzy patch of Andromeda was indeed an island universe of its own, a separate galaxy floating in the cosmic sea. This single quiet observation shattered the prevailing cosmological model, tearing down the walls of our supposed cosmic island and revealing a boundless ocean teeming with countless other islands. It flung open the doors of our understanding, expanding our perceived universe from a single grand galaxy to a multitude beyond imagining. The universe in that moment became infinitely larger, infinitely grander, and infinitely more mysterious than anyone had dared to truly believe. Yet the universe, in its boundless capacity for surprise, was not content to stop there. It wasn't long after this groundbreaking realization that Hubble made another equally strange and perhaps even more profound observation. As he continued to measure the distances to other galaxies and also to observe their movement, he noticed a peculiar pattern. The galaxies were not simply scattered randomly like dust motes suspended motionless in a vast room. Instead, they appeared to be moving away from us, and not just moving away, but doing so in a very specific way. The further away a galaxy was, the faster it seemed to be receding from us. This was a startling discovery, one that felt profoundly counterintuitive, almost an affront to the long-held human notion of a static, unchanging cosmos. It was as if the universe itself was alive, a dynamic, organic, and relentlessly expanding entity. This observation was so deeply disturbing, so profoundly unsettling to the scientific consensus of the time, that even Albert Einstein, the towering theoretical physicist who had just shaken the very foundations of scientific thought by proposing unimaginable transformations to our entire notions about space and time with his theories of relativity, initially refused to accept it. Einstein, whose groundbreaking work had shown that space and time were not fixed backdrops, but rather fluid, interconnected elements, was nevertheless deeply convinced that our universe in its grand totality must be a static, unchanging entity. The idea of a dynamic, evolving, expanding universe was simply too much, too radical even for his revolutionary mind. In fact, so convinced was he that our universe must be a perfectly balanced, unchanging structure, Einstein famously set out to modify his original elegant equations of general relativity. He added an extra element, a mathematical fudge factor, specifically designed to stabilize the mathematics of the universe, to counteract any tendency for it to expand or contract ensuring it remained perfectly static. This arbitrary addition was called the cosmological constant. For Einstein, the very idea that the universe was actively expanding, swelling outwards with each passing moment, was so distasteful, so contrary to his aesthetic sense of cosmic perfection, that he initially simply could not bring himself to accept it, even when observational evidence began to mount. And yet, despite the weight of such a formidable scientific mind, time itself, coupled with the relentless observations of Edwin Hubble, proved his static model wrong. The universe, in its quiet, relentless unfolding, did not adhere to Einstein's initial preference for stasis. The evidence of expansion became undeniable, making Einstein's carefully inserted cosmological constant, which he later famously called his biggest blunder, utterly unnecessary to explain the universe's behavior. The universe was indeed expanding, a revelation that would pave the way for some of the most profound cosmological theories of the 20th century. This was not merely a scientific correction. It was a profound shift in perspective, moving from a static, timeless view of the cosmos to a dynamic, evolving one where change and movement were fundamental aspects of its very being. The method by which Hubble and other astronomers confirmed this expansion relied heavily on an effect you might already be familiar with in everyday life, the Doppler effect. We most commonly encounter the Doppler effect with sound. Imagine an ambulance siren approaching you. Its pitch sounds higher. As it passes and moves away, the pitch drops, sounding lower. This happens because the sound waves are compressed as the source moves towards you, making the wavelength shorter and the frequency higher, and stretched as the source moves away, making the wavelength longer and the frequency lower. The same principle applies to light. If an object emitting light is moving away from you, the light waves are stretched, making them appear redder, a phenomenon known as redshift. Conversely, if an object is moving towards you, the light waves are compressed, making them appear bluer, a blue shift. Because astronomers knew what frequencies the light from specific elements in distant galaxies ought to be arriving at, they could identify the chemical signatures within the light. Like fingerprints, they could then measure whether those light waves were stretched or compressed. By observing the extent of this redshift, Hubble could precisely calculate their direction of travel and their speed. And what he discovered consistently across virtually all the galaxies he observed was a pervasive redshift. This meant unequivocally that all the galaxies in the universe, or at least all those far enough away to show a measurable effect, were moving away from us. They were receding, like ships sailing away on a vast, expanding ocean. This was not a localized phenomenon. It was a universal trend. Every direction he looked, every distant galaxy he measured, seemed to be part of this grand cosmic departure. It wasn't long then before scientists grasped the profound implication of this universal recession. If all the galaxies were moving away from us now, and had been doing so for billions of years, then logically, at some point in the distant past, they must have all been a whole lot closer together. Imagine reversing the cosmic film, rewinding the grand expansion. The galaxies would draw closer and closer, converging into an increasingly dense, hot state. This startling realization, this elegant, backward extrapolation from observed expansion, was the fertile ground upon which the theory of the Big Bang was truly born and cemented into scientific thought. It wasn't just a hypothetical origin point. It was a logical necessity, stemming directly from the observed movement of the galaxies themselves. The expansion of the universe became the foundational pillar upon which our modern cosmological understanding rests, a silent, continuous echo of that initial cosmic unfurling. The discovery of the expanding universe and the subsequent formulation of the Big Bang theory was a monumental triumph of human ingenuity and observation. It provided a coherent framework for understanding the universe's past and evolution. Yet, as with all great scientific breakthroughs, it also brought forth new questions, new layers of mystery even stranger than the ones it had resolved. And indeed, another strange, almost unsettling fact began to trouble scientists, one that the simple Big Bang model in its initial form couldn't quite account for. It wasn't merely that the galaxies were moving away from us. It was something far more curious, something that defied the intuitive logic of any normal explosion or expansion. They were accelerating away from us. The further away a galaxy was, the faster it was moving, as if some unseen, insidious force was giving them an extra push, propelling them outwards with ever-increasing velocity. Most explosions, whether a firecracker or a supernova, lose momentum over time. Their initial blast might be powerful, but the debris gradually slows down, eventually succumbing to the forces of friction or gravity. Yet in the cosmic arena, it was precisely the opposite. The expansion of the universe was not decelerating, as gravity, the great cosmic attractor, would naturally dictate. Instead, it was speeding up, as if an invisible hand was pressing the accelerator pedal harder and harder. And acceleration, as any physicist will tell you, requires energy. Where was this immense, pervasive energy coming from? What unseen force was defying the expected gravitational slowdown, and instead injecting more and more kinetic energy into the universe's expansion? Nobody seemed to know. This mysterious energy seemed to permeate everywhere to fill the very vacuum of space itself, an undetectable but omnipresent influence pushing the cosmic fabric apart. It was a profound puzzle, a fundamental crack in the otherwise elegant edifice of the Big Bang Theory. This was the cosmic riddle that would eventually lead scientists to propose one of the most enigmatic and revolutionary concepts in modern cosmology: the idea of dark energy, a pervasive repulsive force that would redefine our understanding of the universe's ultimate fate and its fundamental composition. As we gently float through the cosmos, our journey brings us to a remarkable crossroads, a moment where the elegance of scientific theories met the stubborn, perplexing observations of reality. The universe, as we discovered in our last quiet contemplation, was not merely expanding. It was doing so with an unexpected, almost defiant acceleration. This was the strange fact that troubled scientists, a cosmic puzzle piece that simply would not fit into the otherwise beautiful picture painted by the Big Bang Theory. It wasn't just that the galaxies were moving away from us like leaves carried on a river. It was that the river itself was speeding up, pushing those leaves apart faster and faster the further away they drifted. And acceleration, as even a gentle breeze can tell us, requires a continuous input of energy. Where in the vast, seemingly empty stretches of intergalactic space was this immense, ubiquitous energy coming from? This question hung heavy in the cosmic air, a profound gap in our understanding. The universe, it seemed, was performing a trick, revealing a hidden mechanism that defied our most fundamental expectations. Most explosions, whether of fireworks bursting or stars ending their lives in a supernova's blaze, eventually slow down. Gravity, the great cosmic sculptor, tugs at everything, constantly trying to pull matter back together, to decelerate any outward motion. Yet in the grand cosmic arena, the exact opposite was occurring. The expansion was not yielding to gravity's gentle, persistent pull. Instead, it was defying it, gaining speed, as if some invisible, colossal hand was pressing an accelerator pedal harder and harder, ceaselessly. The very fabric of space was stretching, yes, but it was stretching with an ever-increasing velocity, pulling distant galaxies away from each other with a vigor that grew with distance. Nobody, it seemed, had a ready answer. This mysterious force, this source of inexhaustible energy, appeared to permeate everywhere, to fill every crevice and every vast, dark expanse of the universe. It was a silent, unyielding pressure, an undetectable push that seemed to emanate from the very vacuum of space itself. To fill this profound gap in their knowledge, to reconcile the elegant mathematics of general relativity with the startling observational data, scientists were compelled to come up with a bold, almost audacious idea: the concept of dark energy. It was a placeholder name, a label for the unknown, much like early explorers might have marked terra incognita on their maps. It represented a force, an energy that we could not directly see or touch, but whose effects were undeniably imprinted upon the largest scales of the cosmos. As scientists began to apply Einstein's general relativity, his magnificent framework for understanding gravity, as the curvature of spacetime to this expanding model of the universe, and then compared their theoretical predictions to the latest, most precise observational data gathered from distant galaxies, a truly startling picture began to emerge. It was a picture that revealed a profound cosmic imbalance, a missing piece in the universe's grand inventory. The particles that we could see, the ordinary matter that makes up everything we perceive. Stars, planets, dust gas, and even ourselves, what scientists call baryonic matter, accounted for a surprisingly tiny fraction of the universe's total mass-energy content. A mere 5%. Imagine trying to balance your cosmic checkbook and finding a staggering shortfall of 95%. This was the perplexing reality scientists faced. The universe, in its observable form, was overwhelmingly empty, yet its behavior suggested a profound unseen influence. The elegant equations of general relativity, when applied to the observed expansion, simply did not add up if only visible matter was present. There had to be something else, something invisible, something pervasive, influencing the gravitational dance of the cosmos on the grandest scales. This missing 95% was a cosmic void, a silent call for something entirely new to fill the conceptual emptiness. It was the only thing that made sense. Scientists had already been grappling with another mysterious cosmic component for decades: dark matter. They had observed that galaxies' immense swirling collections of billions of stars were rotating much too fast for the visible matter within them to hold them together gravitationally. It was as if these celestial merry-go-rounds were spinning so rapidly that their stars should simply fly off into the void. Yet, they remained intact. The only way to explain this gravitational glue, this invisible scaffolding that held galaxies together, was to posit the existence of a substance that exerted gravity but did not interact with light or other forms of electromagnetic radiation. It was dark in the sense that it did not shine or reflect light, rendering it utterly invisible to our telescopes. And it was matter in the sense that it possessed mass and therefore exerted a gravitational pull. This substance, which they called dark matter, seemed to be congregating strangely, forming vast unseen halos around galaxies, pulling them closer together, exerting a gravitational influence that defied their visible content. Scientists attributed a significant portion of that mysterious 95% shortfall to this enigmatic substance, estimating it to make up about 27% of the total mass energy of the universe. So with dark matter accounting for 27%, and ordinary baryonic matter for 5%, we were still left with a colossal 68% of the universe's total content unaccounted for. And this remaining fraction, this overwhelming majority of the cosmos, presented an even more baffling puzzle. While dark matter was pulling things together, helping to form the gravitational wells where galaxies could reside, the universe was also being pushed apart with increasing speed. This relentless outward push required a different kind of invisible agent, a force that acted in opposition to gravity rather than in concert with it. This remaining 68% of the universe, this dominant yet utterly undetectable and invisible component, had to be the energy responsible for that accelerating expansion. This was the cosmic force that was forcing all things apart, defying gravity's unifying embrace. The mathematics, in their cold logical precision, proved it. Without this immense, pervasive, repulsive energy, the observed acceleration of the universe simply could not be explained. The equations would collapse, the numbers would refuse to align with the empirical data gleaned from the depths of space. This invisible, omnipresent energy became known as dark energy. It was a theoretical necessity, a placeholder for something fundamental that our senses could not perceive, and our current understanding could not fully explain. It was not just a convenient invention. It was the only way to make the universe's behavior, as observed, consistent with the foundational laws of physics we believed to be true. It was a testament to the scientific method's ability to infer the unseen from its profound effects on the visible world. The very notion of dark energy is deeply unsettling, isn't it? It means that the vast majority of our universe is made up of something entirely unknown, something that slips through our grasp like smoke, yet dictates the ultimate fate of all things. It challenges our intuitive understanding of reality, suggesting that the empty space between galaxies is far from empty, but is instead brimming with a potent invisible energy that is actively shaping the cosmos on its grandest scales. It's a humbling realization, a quiet reminder that our universe is far more mysterious, far more intricate, and far more filled with wonder than we could ever have imagined. The search for its true nature has become one of the most pressing and profound quests in modern cosmology, an attempt to illuminate the very darkness that underpins our cosmic existence. Think of the universe as a vast cosmic ocean. We, with our telescopes and our scientific instruments, are like tiny boats sailing on its surface, able to observe the waves, the currents, and the distant shores. For a long time, we thought we understood the ocean's fundamental properties, its depth, its composition, the gravitational pull of the moon upon its tides. But then we noticed something strange. The distant shores were not merely drifting apart as the ocean expanded. They were speeding up, accelerating their departure from us. And this acceleration couldn't be explained by the known currents or by the visible water itself. It was as if there was an immense unseen force bubbling up from the very depths of the ocean, pushing the surface outwards with ever-increasing vigor. This unseen force, this hidden engine of expansion, is what we call a dark energy. It is the mysterious wellspring of cosmic propulsion, forever pushing the boundaries of what is known. The journey to comprehend dark energy is not just a scientific pursuit. It is a philosophical one. It forces us to confront the limits of our perception and the boundaries of our current knowledge. It asks us to accept that the most dominant component of our reality is for now a profound enigma. Yet within this mystery lies a tremendous opportunity for discovery, a beacon for future generations of curious minds to unravel the deepest secrets of the cosmos. The very existence of dark energy suggests that our understanding of the fundamental laws of physics, particularly gravity, might still be incomplete. It hints at new particles, new fields, new dimensions, or perhaps even a subtle modification to Einstein's grand theory of relativity itself. The universe, in its infinite generosity, continues to present us with puzzles that inspire awe and drive us to explore the very edges of possibility. As we ponder this vast unseen force, we are reminded of the inherent humility required in the pursuit of knowledge. We might build the most sophisticated telescopes, devise the most elegant equations, and gather the most precise data, but the universe retains its secrets, revealing them only when it is ready, and often only partially. Dark energy stands as a monumental testament to this truth, an invisible, undetectable, yet omnipresent influence that makes up the overwhelming majority of our cosmic reality. Its presence is inferred, its effects are observed, but its true nature remains shrouded in a profound veil of mystery. It is a force that is quietly, relentlessly shaping the ultimate destiny of all things, pushing galaxies further and further apart, dictating the very future of the cosmos itself. And so we leave this chapter with a deeper appreciation for the invisible ballet that unfolds in the cosmic darkness. A dance between the gravitational pull of dark matter, which gathers the visible galaxies into clusters, and the repulsive push of dark energy, which drives the overall expansion of the universe ever faster. These two unseen titans, comprising the vast majority of existence, engage in a subtle, silent struggle that determines the fate of every star, every planet, and ultimately, every living being that has ever gazed upon the night sky and wondered about its profound secrets. We are living in a universe dominated by the unknown, a universe where the most significant players remain elusive, inviting us to peer ever deeper into the cosmic enigma. As we continue our gentle drift through the cosmic expanse, our minds now touched by the profound revelation of dark energy, that invisible force propelling the universe's accelerated expansion, we arrive at a moment of deep scientific introspection. The universe, in its quiet, relentless unfolding, presents us with puzzles that beckon us to reconsider even our most cherished theories. For a long time, the elegance of Einstein's general relativity provided a near-complete picture of how gravity shaped the cosmos. It was a magnificent tapestry, woven with the threads of space-time matter and energy, predicting the orbits of planets, the bending of starlight, and the majestic dance of galaxies. But the accelerating expansion threw a wrench into this otherwise perfect machinery. Leaving scientists in a profound dilemma, was our understanding of gravity incomplete, or was there something entirely new at play? This particular puzzle, the acceleration of the universe, feels profoundly counterintuitive. Imagine, if you will, standing at the edge of a vast, tranquil lake and tossing a pebble into its glassy surface. You expect the ripples to spread outwards, yes, but also to gradually slow down, diminishing in strength as they travel further from the point of impact. This is how most forces in nature behave. An initial impulse creates a motion, but that motion is then gradually arrested by opposing forces, air resistance, friction, or in the case of the cosmos, gravity. Gravity in its simplest form is an attractive force. It pulls things together. It slows down expansions. It causes apples to fall and planets to orbit. So, the observation that the universe's expansion was not only continuing, but actually speeding up, was akin to tossing that pebble into the lake and watching the ripples not only maintain their speed, but actually accelerate as they reach the distant shores. It was a cosmic defiance of the expected, a profound riddle whispered by the very light from distant galaxies. This acceleration meant that the universe was doing something extraordinary, something that simply couldn't be explained by the known forces and matter within it. It implied that there was a hidden engine, a pervasive, invisible wellspring of energy that was actively counteracting gravity's pull, providing a continuous gentle push that grew stronger with distance. This was the moment when the singular shadow began to truly fall over the elegant Big Bang explanation. While the Big Bang beautifully described the universe's hot, dense beginning and its subsequent expansion, it did not inherently account for an accelerated expansion. It predicted a universe where gravity would cause the expansion to slow down over time, perhaps even eventually leading to a grand Big Crunch, where everything collapses back in on itself. But the data from the distant cosmos painted a different picture, a universe destined not for collapse, but for an ever faster, ever lonelier dispersal. The recognition of this accelerating expansion was a gradual process pieced together from the careful observations of type Ia supernovae. These aren't just any exploding stars. They are cosmic standard candles, much like the Cepheid variables we discussed earlier, but far brighter and thus visible across much greater distances. Imagine a specific type of light bulb, designed by the cosmos itself, that always burns with the same peak intrinsic brightness when it explodes. By observing how dim these supernova explosions appeared from Earth, astronomers could measure their distances with remarkable accuracy. And by measuring their redshift, they could determine how fast the portions of the universe containing these supernovae were expanding. What they found, to their astonishment, was that these distant supernovae were fainter than they should have been if the universe's expansion was slowing down. They were further away than predicted by a decelerating universe, implying that the expansion had been speeding up for billions of years. This discovery, made independently by two different research teams in the late 1990s, led to the groundbreaking realization that the universe's expansion was not just ongoing, but accelerating. It was a moment of profound shock and excitement in the scientific community, earning the Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rees in 2011. This was the indisputable observational evidence that forced scientists to confront the limitations of their existing models. It was clear that some unknown component of the universe was exerting a repulsive gravitational effect, pushing space-time apart rather than pulling it together. This inexplicable acceleration begged the question, what kind of energy could possibly be responsible for such a pervasive growing push? The answer could not be ordinary matter, or even dark matter, as both of these exert a gravitational pull, attracting rather than repelling. This required something fundamentally different, something with a negative pressure, a kind of inherent springiness that would cause it to push outwards as space itself expanded. The term dark energy was coined to describe this mysterious all-pervading force. It was a name that acknowledged both its invisible nature and its profound energetic influence on the cosmos. The implications of this accelerating expansion and the necessity of dark energy to explain it are vast and far-reaching. It fundamentally changes our understanding of the universe's composition. For decades, cosmologists had been trying to account for the total mass and energy of the universe. And while they had grappled with the invisible dark matter needed to explain the rotation of galaxies and the clustering of galaxy clusters, dark energy introduced an entirely new, even more dominant component. It suggested that what we see and can directly measure the stars, planets, galaxies, the luminous tapestry of the cosmos, is but a tiny, almost negligible fraction of the total picture. Imagine, if you will, the universe as an enormous, meticulously crafted balance scale. On one side, you have all the matter we can see, the familiar stuff of stars and planets. On the other side, you have the forces that govern its ultimate fate. For a long time, we thought gravity fueled by ordinary matter and dark matter was the dominant force pulling everything inwards, slowing the cosmic dance. But then, unexpectedly, the scale began to tip dramatically outwards, driven by an invisible force we had never accounted for. This force, dark energy, is not merely a small adjustment. It is the dominant player silently, relentlessly pushing the universe towards an unknown destiny. This profound realization has opened up an entirely new frontier in cosmological research. The nature of dark energy is perhaps the greatest unsolved mystery in physics today. Is it a constant property of space itself, an inherent energy density of the vacuum? Is it a dynamic field changing over time and space? Perhaps a fifth force of nature waiting to be discovered? Or is it something even more exotic? Something that challenges our very understanding of space-time and gravity. The questions are vast, the answers elusive, but the pursuit of them drives humanity's relentless quest to comprehend its cosmic home. The accelerating expansion also forces us to rethink the universe's ultimate fate. If the expansion continues to accelerate indefinitely, then distant galaxies will eventually be pushed so far away so fast that their light will no longer be able to reach us. They will effectively be carried beyond our cosmic horizon, disappearing from our view forever. Our observable universe would gradually shrink, becoming an increasingly lonely island in an ever-expanding sea of darkness. This vision, often referred to as the Big Freeze or Big Rip, depending on the precise behavior of dark energy, contrasts sharply with the earlier Big Crunch scenario, where gravity would eventually win, pulling everything back into a hot, dense singularity. The discovery of accelerating expansion has painted a much bleaker, yet equally awe-inspiring picture of a universe destined for cold, dark, and solitary grandeur. The mystery of dark energy is not just a scientific problem. It is a profound philosophical challenge. It pushes us to confront the limits of our knowledge and the vastness of the unknown. It asks us to humbly acknowledge that the majority of reality operates on principles we currently cannot fathom. This humility, however, is not a defeat. It is an invitation to wonder, to explore, to push the boundaries of human ingenuity in the search for answers. The accelerating expansion driven by dark energy serves as a powerful reminder that the universe holds secrets far grander and more intricate than our current theories can fully encompass. It is a testament to the fact that even as we unravel one layer of cosmic mystery, another deeper layer reveals itself, beckoning us onward. Consider the silence of the cosmos, a silence that seems to stretch infinitely. Within this silence, there is a pervasive energy unseen, unheard, yet profoundly active. It is not like the quiet hum of an electric current that we can feel, nor the gentle pressure of air that we can sense. It is a force that acts on the very fabric of space, pulling it apart silently, continuously, with ever-increasing vigor. This relentless push is not confined to specific regions. It is everywhere, filling the vast voids between galaxies, permeating the very space within our solar system. Though its effects are too subtle to be noticed on smaller gravitationally bound scales, it is a fundamental property of the cosmos, shaping its destiny from the largest to the smallest scales of time. The implications for our understanding of gravity are also profound. Is dark energy a component of gravity itself, a subtle modification to Einstein's equations that manifests on cosmic scales? Or is it an entirely separate entity, a fifth force that interacts with gravity in unexpected ways? These are the questions that now animate the minds of theoretical physicists as they strive to develop new models and theories that can accommodate this enigmatic cosmic push. The accelerating expansion forces us to look beyond our current paradigms, to imagine new possibilities, and to venture into uncharted territory in the realm of fundamental physics. It's a humbling yet exhilarating challenge, pushing the boundaries of human thought. In this quiet contemplation, let us embrace the beauty of this cosmic riddle. The accelerating expansion driven by dark energy is not a flaw in the universe. It is a profound revelation. It shows us that reality is far more complex, far more nuanced, and far more wondrous than we had ever dared to imagine. It is a reminder that the universe is a living, evolving entity, full of surprises and hidden depths. And as we continue our journey, we will explore the various ideas that scientists have proposed to unravel the mystery of dark energy, each one a testament to the incredible ingenuity and persistent curiosity of the human mind. The universe whispers its secrets slowly, sometimes in riddles, but it always rewards those who listen with awe and humility. The accelerating expansion is one such whisper, a profound hint at the true nature of the cosmos, guiding us towards an ever deeper understanding of our place within its grand and mysterious design. As our silent journey through the cosmos continues, having pondered the startling reality of an accelerating universe, we now arrive at a deeper, perhaps even more humbling revelation. The universe in its grand composition is profoundly different from what we can see or directly interact with. The accelerating expansion, this relentless cosmic push, led scientists to a realization so profound, it reshaped our understanding of cosmic inventory. It revealed that the universe, as we perceive it with our instruments and our eyes, is merely a thin, luminous veneer, accounting for only a tiny fraction of its total being. The vast majority of reality, it turns out, is invisible. Imagine, if you will, a vast ancient library filled with countless books. For centuries, we believed we were reading all the stories, deciphering all the knowledge contained within its walls. But then we began to notice strange, unexplained phenomena. Books, floating doors opening by themselves, an unseen force tugging at the very shelves. It became clear that only a tiny fraction of the books, perhaps only the covers, were visible to us. The true content, the vast majority of the stories and information, was somehow hidden, operating in a realm beyond our direct perception. This is akin to the cosmic revelation that has reshaped our understanding of the universe's true composition. The startling truth is that the particles we can see, the familiar matter that makes up everything, from the dust motes dancing in a sunbeam to the majestic swirling arms of a galaxy, what scientists call baryonic matter, constitute only a minuscule portion of the universe's total mass energy content, a mere 5%. Pause for a moment and let that number truly sink in. Everything you have ever touched, seen, or smelled, every star that twinkles in the night sky, every planet, every nebula, every living creature, all of it, the sum total of our tangible reality, makes up just 1/20th of the universe. It's like dipping a tiny thimble into an infinite ocean and assuming that thimble holds all the water there is. This profound shortfall of 95% was and remains a monumental puzzle, a cosmic emptiness in our balance sheet that demanded an explanation. This wasn't just a philosophical musing. It was a mathematical necessity. When scientists applied Einstein's general relativity, that elegant, precise language describing how gravity works by bending space-time, to the observed behavior of the universe, particularly the way galaxies rotate and cluster, and how the universe expands, the numbers simply did not add up if only visible matter was present. The equations screamed for more. There had to be something else, something pervasive and powerful influencing the gravitational dance of the cosmos on the grandest scales. It was the only thing that made sense, the only way to reconcile the precise mathematical predictions with the undeniable real-world observations. And so to bridge this vast conceptual chasm, scientists were compelled to propose the existence of two primary invisible components, dark matter and dark energy. They are the silent architects, the hidden puppeteers guiding the cosmic ballet from behind the scenes. Let's first gently explore the idea of dark matter. For decades before the discovery of accelerating expansion, astronomers had noticed peculiar behaviors in galaxies and galaxy clusters that defied explanation by visible matter alone. Imagine a giant cosmic merry-go-round, a galaxy, spinning rapidly. According to our understanding of gravity, the stars at the outer edges of this spinning disk should be flung off into the void, much like water droplets from a rapidly spinning wheel. Yet they don't. They remain gravitationally bound, moving at speeds that simply shouldn't be possible if only the visible stars and gas were providing the gravitational pull. It was as if there was an immense unseen mass providing extra gravitational glue, holding these cosmic structures together. This invisible scaffolding, this omnipresent gravitational influence, was given the name dark matter. It is dark because it doesn't interact with light or any other form of electromagnetic radiation. We cannot see it, hear it, touch it, or even directly detect it with our most sensitive instruments. It doesn't absorb, emit, or reflect light. It simply is. Yet it does interact gravitationally. It exerts a pull just like ordinary matter, but without ever revealing itself visually. Scientists estimate that dark matter accounts for about 27% of the universe's total mass energy content. This means that for every visible speck of matter in a galaxy, there is roughly 5 times as much dark matter, silently, invisibly holding it together. Think of dark matter as an invisible web or a colossal transparent scaffolding that permeates the universe. It's like the wind, which we cannot see, but whose presence we infer by the way it rustles the leaves and pushes the sails of a ship. Similarly, dark matter's presence is inferred by its profound gravitational effects on the visible cosmos. It causes galaxies to rotate faster than they should. It makes galaxy clusters more massive than their visible contents suggest. And it even influences the way light from distant objects bends as it travels through space. This gravitational lensing, as it's called, is like looking through a warped pane of invisible glass distorted by the unseen mass of dark matter. This invisible substance, this missing mass, seems to be congregating strangely, forming vast unseen halos around galaxies, pulling them closer together, creating the cosmic architecture upon which visible galaxies are built. It's the silent foundational force that sculpts the large-scale structure of the universe, forming the cosmic web of filaments and voids that we now observe. But even with dark matter 27% and ordinary baryonic matter 5% accounted for, we are still left with a colossal 68% of the universe's total mass energy content that is utterly unexplainable by any form of matter at all. This remaining overwhelming majority of the cosmos presented an even more baffling puzzle. While dark matter was pulling things together, providing the gravitational wells where galaxies could reside, the universe was simultaneously and paradoxically being pushed apart with increasing speed. This relentless outward push required a different kind of invisible agent, a force that acted in direct opposition to gravity rather than in concert with it. This was the territory of the truly enigmatic. This remaining 68% of the universe, this dominant, yet utterly undetectable and invisible component, had to be the energy responsible for that accelerating expansion. This was the cosmic force that was defying gravity's unifying embrace, silently, persistently, forcing all things apart. It wasn't matter pulling, it was energy pushing. This pervasive repulsive energy became known as dark energy. It's a theoretical necessity, a placeholder for something so fundamental, so pervasive that our senses cannot perceive it, and our current understanding can only infer its existence through its profound cosmic effects. The mathematics in their cold, logical precision proved it. Without this immense, pervasive, repulsive energy, the observed acceleration of the universe simply could not be explained. The elegant equations of Einstein's general relativity, when combined with the precise observational data of supernovae and the large-scale structure of the universe, demanded its presence. The numbers would collapse, the models would fail to align with the empirical truth gleaned from the depths of space. Dark energy was not just a convenient invention, a mere theoretical patch to fix a problem. It was the only way to make the universe's observed behavior consistent with the foundational laws of physics that we believe to be true. It was a testament to the scientific method's ability to infer the unseen from its profound and undeniable effects on the visible world, a journey from perplexing observation to a bold yet necessary theoretical postulate. The very notion of dark energy is deeply unsettling, isn't it? It implies that the vast majority of our universe is made up of something entirely unknown to us, something that slips through our grasp like smoke yet dictates the ultimate fate of all things. It challenges our intuitive understanding of reality, suggesting that the empty space between galaxies is far from empty, but is instead brimming with a potent, invisible energy that is actively shaping the cosmos on its grandest scales. It's a humbling realization, a quiet reminder that our universe is far more mysterious, far more intricate, and far more filled with wonder than we could ever have imagined in our wildest dreams. The search for its true nature has become one of the most pressing and profound quests in modern cosmology, an attempt to illuminate the very darkness that underpins our cosmic existence and to truly understand the majority of our universe. Consider the universe not as a collection of objects, but as a dynamic interplay of forces and components. We have the familiar baryonic matter, the stardust and atoms like the notes in a cosmic symphony, forming the melodies we can hear and see. Then there's dark matter, the invisible conductor, providing the structure and gravitational framework, ensuring the instruments stay in tune and the orchestra doesn't fly apart. And finally, there is dark energy, the unseen, unheard crescendo, a relentless growing force that is amplifying the sound, speeding up the tempo, pushing the very boundaries of the performance outwards with ever-increasing intensity. It is the dominant force, the ultimate arbiter of the cosmic narrative, subtly yet profoundly influencing every aspect of its future. This realization that our universe is composed of roughly 5% ordinary matter, 27% dark matter, and a staggering 68% dark energy is the standard model of cosmology often referred to as the lambda CDM model. Lambda L represents the cosmological constant, a leading candidate for dark energy, and CDM stands for cold, dark matter. This model is currently the best fit for all cosmological observations, from the cosmic microwave background radiation, the afterglow of the Big Bang, to the large-scale distribution of galaxies. It's a powerful framework, but it comes with a profound caveat. Two of its three main ingredients remain fundamentally mysterious. We understand their effects, we know how much of them there must be, but their true nature remains elusive. The existence of dark energy suggests a universe far more active and dynamic in its empty spaces than previously conceived. It hints that the vacuum of space, often thought of as nothingness, might in fact be teeming with latent energy capable of exerting a powerful, repulsive force. This is not just a scientific problem. It is a profound philosophical challenge. It pushes us to confront the limits of our perception and the boundaries of our current knowledge. It asks us to humbly acknowledge that the majority of reality operates on principles we currently cannot fathom. This humility, however, is not a defeat. It is an invitation to wonder, to explore, to push the boundaries of human ingenuity in the search for answers. The accelerating expansion driven by dark energy serves as a powerful reminder that the universe holds secrets far grander and more intricate than our current theories can fully encompass. It is a testament to the fact that even as we unravel one layer of cosmic mystery, another deeper layer reveals itself, beckoning us onward. And so, as we conclude this chapter, we are left with a new, more comprehensive picture of our cosmic home, albeit one dominated by shadow. We now understand that the beautiful luminous galaxies we gaze upon are but mere sparks in a vast unseen ocean. This is a universe where the familiar is the exception and the mysterious is the rule. The dance between ordinary matter, and dark energy is the true cosmic ballet, a silent, continuous performance whose music we are only just beginning to discern. We continue our journey into the heart of these mysteries, ever curious, ever humbled by the sheer scale and profound enigma of the cosmos. The search for the true nature of dark energy, that ultimate puzzle, is one of the grandest quests of our time, a quest that promises to unlock secrets that could redefine our very understanding of existence. Our gentle exploration of the cosmos now brings us to a fascinating point, grappling with the very nature of dark energy itself. Having understood its profound effect, the accelerating expansion of the universe, the next logical and perhaps most challenging step is to ask, what is it? This question has given rise to a few different ideas, each a testament to the ingenuity and sometimes the desperation of scientific thought when faced with a truly monumental mystery. These are not definitive answers, but rather pathways of inquiry, whispers of possibility in the grand cosmic silence. One of the most intriguing ideas, a ghost from the past, that has surprisingly re-emerged in a new guise, is Einstein's cosmological constant. You might remember we touched upon this earlier when Einstein, initially resistant to the idea of an expanding universe, inserted this mathematical term into his equations of general relativity. His original intention was to act as a kind of cosmic counterbalance, a push to perfectly counteract gravity's pull, thereby ensuring a perfectly static, unchanging universe, a universe that neither expanded nor contracted. It was a term designed to maintain a delicate equilibrium, a mathematical stabilizer for a cosmos he believed to be timeless and immutable. However, as Edwin Hubble's observations overwhelmingly confirmed the universe was indeed expanding, Einstein famously discarded this constant, purportedly calling it his biggest blunder. For decades, it lay dormant, a relic of a beautiful, but ultimately incorrect cosmic vision. Yet, in a remarkable twist of fate, the accelerating expansion of the universe breathed new life into this old idea. What if Einstein's cosmological constant wasn't a blunder after all, but rather a profound, albeit misunderstood, premonition? What if it wasn't there to stop expansion, but to cause acceleration? The concept of a cosmological constant, if interpreted as a form of dark energy, suggests that the vacuum of space itself possesses an inherent unchanging energy density. Imagine that seemingly empty space is not truly empty at all, but is instead brimming with a latent uniform energy, an intrinsic property of the cosmos. This energy would be like an invisible, ubiquitous fluid that exerts a constant outward pressure, pushing the very fabric of space apart. The crucial aspect of this vacuum energy, as it's sometimes called, is that as space expands, more of this empty space is created, and therefore more of this inherent vacuum energy comes into existence. It's a self-perpetuating push. More space means more vacuum energy, which in turn creates more space, leading to an accelerating expansion. This idea has an elegant simplicity. It's a single number unchanging throughout cosmic history, built directly into the fundamental equations of the universe. If you start with a bigger cosmological constant, you'd naturally get a universe that tipped into constantly accelerating away from itself. Just like the observations tell us we see in real life, it provides a straightforward, albeit mysterious explanation for the cosmic acceleration. Einstein himself, in one of his later more prescient thoughts, hypothesized that empty space might not truly be nothing, but that it held energy, and crucially, that this energy could and did create more of itself as space expanded. This profound insight, though speculative at the time, perfectly aligns with the revived concept of the cosmological constant as dark energy. The continuous creation of space would, by this mechanism, create more of this vacuum energy, thereby increasing the pushing power as time went on, ensuring a relentless, ever-accelerating expansion. However, despite its elegance, there's a profound why that remains unanswered. It's unclear why space would have this property at all. Why should the vacuum possess an inherent energy density? The cosmological constant in this context is more a recognition that the universe seems to have this property, rather than a deep explanation of its fundamental origin. It's like observing a ball rolling uphill and concluding there must be an invisible ramp without understanding what built the ramp or why it's there. It describes what is happening, but not why it's happening, or where this inherent energy comes from at a more fundamental level. This lack of a deeper theoretical underpinning is a significant challenge for the cosmological constant hypothesis. It remains a magnificent mathematical fit for the observational data, but its physical origin is shrouded in mystery, a silent given in the cosmic equations. It offers a powerful how, but a silent why. To try and fill this theoretical gap, another branch of physics, the enigmatic realm of quantum mechanics, stepped up to the plate, offering a different, albeit equally perplexing perspective. Quantum mechanics describes the bizarre and counterintuitive behavior of matter and energy at the smallest subatomic scales. In the quantum world, even a perfect vacuum, what we perceive as utterly empty space, is far from inert. It's a bustling, effervescent sea of activity, a vibrant, restless hum. Scientists of this school hypothesized that perhaps virtual particles were to blame for this extra energy. Imagine a quiet ocean that looks perfectly calm and still from above its surface, unruffled and serene. But deep below the surface, hidden from plain sight, it teems with a hidden, frantic life, with countless tiny creatures constantly flickering in and out of existence, never quite making it to the surface yet, their collective activity creating a subtle underlying pressure. This is a bit like the quantum vacuum. Even in the deepest void of space, quantum mechanics predicts that virtual particles are constantly popping into existence, seemingly from nothingness, as a work of the quantum wave function that exists everywhere. These virtual particles are fleeting phantom pairs of particles and their corresponding antiparticles that literally borrow energy from the vacuum for an infinitesimally brief moment before almost immediately annihilating each other and vanishing back into the vacuum from which they came. They don't stick around for long, like tiny ephemeral bubbles that briefly surface and then pop. But here's the intriguing part. In the brief, almost immeasurable moment before their annihilation, these virtual particles could conceivably push against things, exerting a minuscule momentary force. If this endless, furious flickering of virtual particles were happening across the entire vastness of space, the cumulative effect of their tiny fleeting pushes could in theory generate a pervasive outward pressure, a form of dark energy. This theory had some experimental evidence to back it up, at least in a limited form. There is indeed some suggestion that virtual particles do in fact exist, at least in some forms, and their effects can be indirectly observed in phenomena like the Casimir effect, where two uncharged parallel metal plates placed very close together in a vacuum. Experience a tiny attractive force due to the subtle pressure difference created by virtual particles outside pushing the plates together while those between them are suppressed. However, the promise of this quantum explanation quickly ran into a formidable, almost comically large problem. When scientists tried to work out how much energy such particles could create if this frantic continuous activity was happening in the vacuum of space, the answer proved to be too large. And not just by a little bit, not by a factor of 2 or 10 or even 1,000. The calculated energy density was larger than the observed dark energy density by a mind-boggling factor of 10 to the power of 120 tant, followed by 120 zeros. This gargantuan discrepancy is so immense that it borders on the absurd. It's like trying to calculate the weight of a feather and getting an answer that's heavier than all the stars in the universe combined. When your answer is too big by 120 zeros, there's likely something fundamentally wrong with your maths, or perhaps more accurately, with your understanding of how quantum mechanics and gravity truly interact at a fundamental level. Indeed, this jaw-dropping answer got the dubious accolade as the worst theoretical prediction in the history of physics. It was a stark reminder that while quantum mechanics is incredibly successful at explaining the very small its direct application to the energy of the vacuum, and thus to dark energy, leads to a profound and unresolved paradox. This monumental failure of the quantum vacuum energy calculation left physicists searching for alternative explanations, leading to a third main idea, that of a varying cosmological constant. This concept suggests that dark energy is not truly a constant fixed value embedded in the fabric of space, but rather a dynamic adjusting field. Imagine it not as a static, unchanging pressure, but more like an electrical field or gravitational field that can change its strength and influence over time and space. This theoretical force, this dynamic field responsible for the repelling force throughout space, was given the poetic name quintessence. The word itself means the fifth essence, hearkening back to ancient Greek philosophy, where it referred to a pure fundamental substance, distinct from the four classical elements of earth, air, fire, and water. If quintessence really does exist, it might represent a fifth fundamental force of existence, joining the familiar quartet of gravity, electromagnetism, and the strong and weak nuclear forces. The idea of quintessence offers a potential solution to the why problem that plagues the cosmological constant. If dark energy is a dynamic field, then its properties, its strength, and its behavior could theoretically evolve over cosmic time, perhaps even explaining why it started to dominate the universe's expansion only relatively recently. It allows for a richer, more complex interplay of cosmic forces. Perhaps in the early universe, this quintessence field was weak, allowing matter and radiation to dominate. But over billions of years as the universe expanded and cooled, the quintessence field could have evolved, becoming stronger and eventually dominating the expansion, leading to the acceleration we observe today. However, the problem with this idea, the same as the issue with the cosmological constant, is that there is no clear explanation as to why it exists or what its fundamental properties are. What is this quintessence field made of? How does it interact with other particles and forces? Why does it behave in the way it's hypothesized to behave? We have no fundamental theory that predicts its existence or its specific characteristics. It remains a theoretical construct, an elegant mathematical possibility, but one still awaiting a deeper physical justification. It shifts the mystery from why does the vacuum have energy to why does this new field exist and behave as it does? While it offers more flexibility than a fixed cosmological constant, it introduces its own set of fundamental unknowns. In short, this is still a very poorly understood field of study. The true nature of dark energy remains one of the most profound and vexing mysteries in modern physics and cosmology. Each proposed idea, the cosmological constant, quantum vacuum energy, and quintessence, offers a plausible mechanism for the accelerating expansion. but each also comes with its own set of deep, unanswered questions. More information, more observational data, and profound theoretical breakthroughs would be needed before accurate and definitive conclusions can be drawn about the true identity of this elusive cosmic force. The universe, in its boundless generosity, offers us a canvas of awe and wonder, but it also presents us with these monumental riddles. Dark energy is not just a scientific problem. It's a testament to the fact that the cosmos holds depths of mystery we are only just beginning to plumb. It forces us to acknowledge the vastness of our ignorance, even as we celebrate the triumphs of our knowledge. The search for dark energy's true nature is not merely a quest for a scientific answer. It is a profound journey into the very heart of reality, a humble acceptance that the universe is far stranger, far more complex and far more wonderful than our current understanding can fully grasp. It reminds us that the grand cosmic story is still being written, and we are but curious readers eagerly turning each new mysterious page. Our journey through the cosmos has brought us to the very edge of our scientific understanding, peering into the profound mystery of dark energy. We have explored the notion that it might be an inherent property of space, a quantum hum, or a dynamic field. Yet as we've seen, each of these theoretical whispers leads to more questions than answers. This is where the universe, in its boundless enigma, gently reminds us of the limitations of our current perception. Spotting something invisible is quite naturally extraordinarily hard. It's like trying to grasp moonlight or capture the scent of a dream. How do you detect something that doesn't interact with light, that slips through our conventional instruments without leaving a trace save for its monumental gravitational push? Yet humanity's curiosity is a relentless force, unwavering in the face of such profound challenges. If we cannot directly see dark energy, we can perhaps observe its impact on the universe around us. This is the ingenious approach adopted by scientists across the globe to study dark energy, not by looking for it directly, but by meticulously mapping the subtle distortions, the accelerated stretches, and the grand cosmic patterns it imprints upon the visible tapestry of galaxies and matter. It's like inferring the presence of an unseen giant by observing the way the trees sway in its invisible wake, or the mighty currents it creates in a vast, distant ocean. This indirect but powerful method of investigation is already well underway, with different observatories and scientific collaborations attempting this grand cosmic detective work in various ingenious ways. One such ambitious endeavor involves looking into the vast, dark patches of space that lie between galaxies. Here, far from the blinding light of stars, the universe reveals its more subtle patterns. In São Paulo, Brazil, a ground-based radio telescope known as the Bingo telescope, short for Baryon Acoustic Oscillations from the Integrated Neutral Gas Observations Telescope, is embarking on a unique quest. Its mission is to monitor the radiation given off by hydrogen atoms in these cosmic voids. Hydrogen, the most abundant element in the universe, is a silent narrator of cosmic history, even in its most diffused and faint forms. By observing the faint radio waves emitted by these lonely hydrogen atoms, Bingo intends to create a map of their distribution, searching for any unusual distributions of matter that might point to the influence of dark energy. This approach hinges on a curious fact about the universe: matter doesn't just spread out randomly. Instead, it clusters in waves, forming a vast, intricate cosmic web of filaments and voids. Imagine dropping a stone into a still pond. Ripples spread outwards, creating concentric circles. In the early universe, immediately after the Big Bang, similar ripples, Baryon Acoustic Oscillations, BAOs, were imprinted upon the primordial plasma. These were sound waves, acoustic waves that propagated through the hot, dense soup of matter and radiation before the universe cooled enough for atoms to form. As these waves traveled, they dragged matter along with them, creating regions of slightly higher density and slightly lower density. When the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms, an event known as recombination occurring about 380,000 years after the Big Bang, the universe suddenly became transparent to light. At this point, the sound waves effectively froze in place, leaving behind a characteristic pattern of density fluctuations in the distribution of matter. It's thought that this is to do with those ripples in the early universe right after the Big Bang that have coalesced into more solid forms of matter as the universe cooled, locking those ripples into place. These frozen ripples manifest today as a preferred distance between galaxy clusters. Statistically, it is much more likely that there is a distance of around 500 million light-years between any two galaxies than any other number. This cosmic ruler, derived from the scale of these ancient sound waves, provides a powerful tool for measuring the universe's expansion history. By precisely mapping the distribution of hydrogen gas in the vast cosmic voids, using telescopes like BINGO, scientists can identify these baryon acoustic oscillations. If dark energy is indeed causing the expansion to accelerate, it would suddenly stretch this cosmic ruler, making the observed distance between these preferred clusters appear larger than expected for a universe without accelerating expansion. Seeing the gaps between such ripples, even in the darkest corners of space, could be very instructive. It's like observing how a pattern drawn on a balloon stretches as the balloon inflates. The stretching tells you about the inflation's speed. BINGO's quest, therefore, is to precisely measure these subtle stretches, providing invaluable data on how dark energy has been influencing the cosmic expansion over billions of years. It's a painstaking but deeply insightful approach, listening to the faintest whispers of hydrogen in the cosmic night to discern the invisible hand of dark energy. However, if you truly want to spot dark energy's hand over time and space, to track its influence not just as a static effect, but as a dynamic force that might have changed throughout cosmic history, you need to go big. You need a tool capable of observing an immense volume of the universe with exquisite detail, stretching back billions of years into the cosmic past. And it's for precisely that purpose that the European Space Agency ESA has just launched the magnificent Euclid Space Telescope. Euclid is not merely a telescope. It is a cosmic cartographer designed to map the universe with a precision and scope previously unimaginable. Euclid is a wide-angle telescope, meaning it can capture vast swathes of the sky in a single glance, allowing it to survey an enormous portion of the cosmos efficiently. It is equipped with a 600-megapixel camera, an incredibly powerful eye designed to capture both visible light and infrared radiation. This dual capability is crucial because visible light allows it to observe closer, brighter galaxies, while infrared radiation can penetrate the cosmic dust and allows it to peer further back in time, seeing the light from more distant redshifted galaxies, whose visible light has been stretched into the infrared spectrum by the universe's expansion. Euclid's mission is to survey over a third of the sky, an immense cosmic canvas with a level of detail and sharpness that is 4 times greater than previously achieved by ground-based telescopes. Imagine creating a photograph of an entire continent, but with enough resolution to discern individual blades of grass. That is the ambition of Euclid. Euclid's central objective is not just to take pretty pictures. It wants to map everything going back 10 billion years. This means observing galaxies as they were when the universe was only about a quarter of its current age, providing a detailed snapshot of cosmic structure throughout most of the universe's history. The hope is that in so doing, by meticulously charting the positions and shapes of billions of galaxies across this vast cosmic timeline, it'll be possible to create a 3D map of the influence of dark energy. By observing how these galaxies are distributed, and how their shapes are subtly distorted by the gravitational lensing effects caused by intervening dark matter, and the expansion of space scientists can precisely measure the universe's expansion rate and its acceleration at different epochs in cosmic history. This 3D map will provide unprecedented insights into how dark energy's influence has changed or remained constant over all that time. Is dark energy truly a constant, as the cosmological constant hypothesis suggests? Or is it a dynamic field like quintessence, whose strength has varied over billions of years? Euclid is poised to provide the data to answer these profound questions. While Euclid will also look at individual stars too, especially in nearby galaxies, its main objective is sheer volume. It is a survey mission designed to gather statistical data from an enormous number of galaxies, allowing scientists to discern subtle patterns and trends that would be invisible if they focused only on individual objects. This way, the subtle, pervasive pattern of dark energy will hopefully emerge, revealing its true nature through its cumulative effects on the largest structures in the universe. It's like trying to understand the flow of an entire ocean by tracking the movement of millions of tiny currents and eddies, rather than just focusing on one single wave. The sheer statistical power of Euclid's data will be its greatest asset. The Euclid mission represents a monumental leap in our ability to probe the cosmic dark. It launched on the 1st of July 2023 and has since gracefully arrived in its designated L2 Lagrange point. A Lagrange point is a special region in space where the gravitational forces of two large bodies, in this case the Sun and Earth, balance, allowing a spacecraft to hover in a stable position with minimal fuel expenditure. L2 specifically is a spot about 1.5 million kilometers, nearly a million miles beyond Earth, away from the Sun, making it an ideal location for telescopes that need a stable, cold, and dark environment to observe the distant universe without interference from Earth's light or heat. Euclid has already started taking its first images. Although these early photos of starscapes and galaxies are only tests and do not represent the full levels of fidelity Euclid will be able to manage once it has finished its meticulous tuning and calibration process. Like a concert piano, a complex space telescope requires precise adjustments before it can play its full resonant cosmic symphony. Once the calibration process is complete, however, Euclid will embark on its ambitious 6-year mission to map out our stars, and more importantly, to hopefully answer important questions like what is the nature of dark energy, and whether our understanding of the laws of gravity is really complete. It is a mission steeped in profound hope, a testament to humanity's unyielding drive to comprehend the universe that cradles us. So fingers crossed that this mission can shed some light on the mystery that is dark energy. For now, though, this enigmatic force remains a profound mystery, a cosmic shadow that shapes our destiny. It's only because of the universe's accelerating expansion that we are aware of it at all. It is otherwise utterly undetectable through direct means. Yet despite its elusive nature, its impact is undeniable and overwhelmingly dominant. As we've discussed, it makes up over 60% of all that exists in the universe in terms of mass energy. This means it must be around us all right now, a pervasive, invisible presence. It pushes on us gently, subtly, just as it pushes on every other galaxy, every star, every planet, every particle. Slowly but surely, it forces all things apart, ever so gradually increasing the distances between cosmic structures, dictating the ultimate cosmic ballet. The very fact that dark energy is so pervasive yet so elusive underscores the grand challenge it presents. It forces us to rethink our assumptions about the very fabric of reality. Is the vacuum truly empty? Are there more fundamental forces at play than we currently understand? Euclid and missions like Bingo are designed to collect the subtle clues, the faint echoes, the gravitational imprints that dark energy leaves behind. They are like cosmic archaeologists, piecing together the story of an unseen force from the subtle changes it has wrought over billions of years and billions of light years. The data they collect will be meticulously analyzed, sifted through for patterns, anomalies, and statistical significance. Every faint galaxy, every subtle distortion in the light from a distant quasar, every precise measurement of the cosmic ruler from baryon acoustic oscillations will contribute to building a more complete picture of this enigmatic force, the quest to understand dark energy is not just about filling a gap in our cosmological models. It's about pushing the boundaries of fundamental physics. It might require us to revise Einstein's theory of general relativity, the most successful theory of gravity we have. Or it might lead to the discovery of new particles, new fields, or even extra dimensions that interact with our familiar universe in unexpected ways. The implications are staggering, potentially leading to a revolution in our understanding of space-time and the very nature of reality. The universe is a grand laboratory, and dark energy is its most profound experiment, playing out on cosmic scales over billions of years. And so we watch and we wait with bated breath as Euclid begins its long, arduous task. It is a testament to the enduring human spirit of inquiry, our unyielding desire to understand the universe that cradles us. The answers it finds or the new questions it raises will undoubtedly shape the future of cosmology for decades to come. The cosmos continues its silent, relentless expansion, driven by this mysterious force. We are but tiny observers on a speck of dust, yet our minds reach out striving to grasp the boundless invisible hand that guides the cosmic dance. Our quiet journey through the universe has led us to the grand stage where the cosmos performs its most enigmatic ballet. We have sensed the invisible presence of dark energy, that pervasive force silently accelerating the universe's expansion. Now our focus shifts to the ingenious methods scientists employ to unmask this elusive entity, methods that rely not on direct detection, but on deciphering the subtle patterns and whispers it imprints upon the visible cosmic tapestry. Spotting something truly invisible is, of course, a challenge of immense proportions. It's akin to trying to see the wind itself, rather than merely its effects on a rustling leaf or a bending tree. Yet our human ingenuity, driven by an unyielding curiosity, finds ways to infer the unseen from its profound influence on the seen. The approach is akin to cosmic archaeology, piecing together the story of an unseen force from the ancient artifacts it leaves behind, in the form of galactic distribution and the subtle distortions of light from distant sources. This meticulous detective work is already well underway with diverse observatories across the globe, both on Earth and in space, each contributing a unique piece to this grand overarching puzzle. Each instrument, each meticulously collected data point, represents a whisper from the past, a clue in the grand cosmic riddle of dark energy. One particularly fascinating method involves looking into the vast, seemingly empty stretches of space that lie between galaxies. Here, far from the blinding glare of stars and the dense clusters of galactic cities, the universe reveals its more subtle primordial patterns. In the quiet rolling hills of São Paulo, Brazil, a remarkable ground-based instrument known as the Bingo telescope, an acronym that rolls off the tongue like a gentle tune, standing for Baryon Acoustic Oscillations from the Integrated Neutral Gas Observations Telescope, is embarking on a unique and ambitious quest. Its mission is to listen to the faint ancient radio waves emitted by the most abundant element in the universe, hydrogen atoms. Even in their most diffused and solitary forms, these hydrogen atoms, scattered sparsely throughout the cosmic voids, carry echoes of the universe's infancy, silent narrators of cosmic history. Bingo is not looking for bright sparkling objects. Instead, it intends to monitor the radiation given off by these hydrogen atoms in the vast, dark patches of space between galaxies. By meticulously mapping their precise distribution across the cosmos, Bingo aims to identify any unusual distributions of matter that might point to the influence of dark energy. This particular approach hinges on a concept both subtle and profoundly revealing, the phenomenon of baryon acoustic oscillations, or BAOs. To understand BAOs, let us conjure a gentle image of the early universe, not as a silent void, but as a dense, incredibly hot and turbulent cosmic soup. Imagine dropping a stone into a perfectly still pond. Ripples spread outwards, creating concentric circles that move gracefully across the water's surface. In the universe's infancy, just moments after the Big Bang, similar ripples, powerful sound waves, propagated through the primordial plasma, which was a unified hot mixture of matter and radiation. As these sound waves traveled outwards, they dragged matter along with them, creating regions of slightly higher density and slightly lower density, much like the peaks and troughs of waves on a pond. This cosmic sound was not just a fleeting echo. When the universe was only about 380,000 years old, a mere blink in cosmic time, it cooled enough for electrons and protons to finally combine and form neutral hydrogen atoms. This pivotal event, known as recombination, had a profound consequence. The universe suddenly became transparent to light. Before recombination, the dense plasma was opaque, like a thick fog. After recombination, light could travel freely, and the sound waves previously propagating through the plasma essentially froze in place. They left behind a characteristic fossilized pattern of density fluctuations, subtle variations in the distribution of matter, imprinted upon the very fabric of the cosmos. It's thought that this is to do with those ripples in the early universe, right after the Big Bang, that have coalesced into more solid forms of matter as the universe cooled, locking those ripples into place, forming the earliest seeds of cosmic structure. These fossilized sound waves manifest today as a preferred distance between galaxy clusters. Statistically, when we look across the vastness of the universe, we find that it is much more likely that there is a distance of around 500 million light-years between any two galaxies than any other number. This fixed scale, imprinted in the primordial universe and stretched by its subsequent expansion, acts as an incredibly precise cosmic ruler. Imagine this ruler as a measuring tape laid across the expanding universe. If the universe's expansion were slowing down, the marks on this ruler would appear closer together over cosmic time. But if the expansion is accelerating, as dark energy suggests, then this cosmic ruler would appear to be subtly stretched, making the observed distance between these preferred galaxy clusters seem larger than expected at later times. Bingo's quest, therefore, is to precisely measure these subtle stretches by painstakingly mapping the distribution of hydrogen gas in the vast cosmic voids. By identifying the scale of these ancient baryon acoustic oscillations in different epochs of cosmic history, scientists can gather invaluable data on how dark energy has been influencing the cosmic expansion over billions of years. It's a painstaking but deeply insightful approach, akin to listening to the faintest whispers of ancient hydrogen in the cosmic night to discern the invisible hand of dark energy. The strength of BAO measurements lies in their reliability, since the initial scale of these sound waves is so well understood from the physics of the early universe. Any deviation from that scale in the modern universe can be directly attributed to the effects of dark energy and the universe's expansion history. This method provides an independent and powerful way to confirm and characterize the accelerating expansion. However, to truly unravel the intricate dance of dark energy and trace its hand over time and space, to determine if its influence has remained constant or if it has varied throughout cosmic history, you need to go big. You need a tool capable of observing an immense volume of the universe with exquisite detail, a cosmic eye that can peer back billions of years into the universe's deepest past. And it's for precisely that monumental purpose that the European Space Agency ESA has just launched the magnificent Euclid Space Telescope. Euclid is not merely another telescope. It is a dedicated cosmic cartographer designed to map the universe with a precision and scope previously unimaginable. Imagine not just photographing a landscape, but creating a three-dimensional model so detailed you can measure every hill and valley, every tree and stone. That is the ambition of Euclid. It is specifically designed as a wide-angle telescope, meaning it can capture vast swathes of the sky in a single efficient glance. This allows it to survey an enormous portion of the cosmos much more quickly than conventional telescopes with narrower fields of view. At its heart, Euclid is equipped with an incredibly powerful eye, a 600 megapixel camera that is designed to capture both visible light and infrared radiation, This dual capability is absolutely crucial for its mission. Visible light allows Euclid to observe closer, brighter galaxies, providing a crisp view of the more recent universe. However, as light from more distant galaxies travels through the expanding universe, its wavelengths get stretched, shifting from the visible spectrum into the infrared spectrum, a phenomenon known as redshift. By being able to detect infrared radiation, Euclid can effectively peer further back in time, seeing the light from these ancient, highly redshifted galaxies, as they were billions of years ago when the universe was much younger. This allows Euclid to create a comprehensive timeline of cosmic evolution. Euclid's ambitious mission is to survey an immense cosmic canvas covering over a third of the sky. This is an astonishing area to cover with such detail. It will achieve a level of detail and sharpness that is 4 times greater than previously achieved by ground-based telescopes. While ground-based telescopes are powerful, their views are always blurred and distorted by Earth's turbulent atmosphere. Euclid, operating in the pristine vacuum of space, can achieve unparalleled clarity, allowing it to precisely measure the subtle shapes and positions of billions of distant galaxies. The central goal of Euclid's mission is not just to take pretty pictures, but to meticulously map everything going back 10 billion years. This means observing galaxies as they were when the universe was only about a quarter of its current age, providing an unprecedented detailed snapshot of cosmic structure throughout most of the universe's evolutionary history. By charting the precise positions and shapes of these billions of galaxies across this immense cosmic timeline, it'll be possible to create a revolutionary 3D map of the influence of dark energy. This map will not just show where galaxies are now, but how their distribution has evolved and how their shapes have been subtly distorted by the gravitational lensing effects caused by intervening dark matter and, crucially, by the accelerating expansion of space itself. This 3D map will provide an unparalleled window into how dark energy's influence has changed or remained constant over all that time. This is the key question that will differentiate between competing theories of dark energy. If dark energy is truly a constant property of space, as the cosmological constant hypothesis suggests, then its influence should be unchanging throughout cosmic history. However, if it is a dynamic field like quintessence, whose strength can evolve, then Euclid's data might reveal subtle variations in its power over billions of years. Euclid is perfectly poised to provide the definitive data needed to answer these profound questions, potentially confirming one of the existing theories, or perhaps even more excitingly, revealing something entirely new and unexpected. While Euclid will also look at individual stars, too, especially in nearby galaxies, to calibrate its instruments and refine its measurements, its primary objective is sheer volume. It is a survey mission designed to gather statistical data from an enormous number of galaxies. This statistical approach is crucial because the effects of dark energy are often subtle on individual objects, but become apparent when looking at the collective behavior of billions of galaxies. By analyzing these vast data sets, scientists can discern subtle patterns and trends that would be utterly invisible if they focused only on individual objects. This way, the subtle, pervasive pattern of dark energy will hopefully emerge, revealing its true nature through its cumulative effects on the largest structures in the universe. Much like a grand, intricate mosaic reveals its full picture only when viewed from afar, the Euclid mission represents a monumental leap in our ability to probe the cosmic dark. It launched on the 1st of July 2023, a day etched into the annals of space exploration, and has since gracefully and precisely arrived at its designated L2 Lagrange point. A Lagrange point is a special gravitationally stable location in space where the gravitational forces of 2 large celestial bodies, in this case, the Sun and Earth, balance each other out. This allows a spacecraft to hover in a stable position with minimal fuel expenditure, much like a boat finding a calm spot in a turbulent current. Specifically, the L2 point, located about 1.25 million kilometers, nearly a million miles beyond Earth away from the Sun, is an ideal location for space telescopes. It provides a stable cold and dark environment, free from the interference of Earth's light heat and atmospheric distortions, allowing Euclid to observe the distant universe with unparalleled clarity and sensitivity. Euclid has already started taking its first breathtaking images, providing tantalizing glimpses of its future capabilities. However, these early photos of distant starscapes and galaxies are primarily tests and do not yet represent the full levels of fidelity and scientific precision Euclid will be able to manage once it has finished its meticulous tuning and calibration process. Like a master musician tuning a complex orchestral instrument, a sophisticated space telescope requires precise adjustments before it can perform its full resonant cosmic symphony. Once the calibration process is complete, however, Euclid will embark on its ambitious 6-year mission to meticulously map out our stars and, more importantly, to hopefully answer important questions like what is the nature of dark energy and whether our understanding of the laws of gravity is really complete. It is a mission steeped in profound hope, a testament to humanity's unyielding drive to comprehend the universe that cradles us and to decipher the silent whispers of its deepest mysteries. So with bated breath and fingers crossed, we await the revelations that this mission may bring, hoping it can shed some much-needed light on the enduring mystery that is dark energy. For now, though, this enigmatic force remains largely shrouded, a cosmic shadow that dictates our ultimate destiny. It's only because of the universe's accelerating expansion, its relentless outward push, that we are aware of dark energy at all. It is otherwise utterly undetectable through any direct means we possess. Yet despite its elusive nature, its impact is undeniable and overwhelmingly dominant. As we've discussed, it makes up over 60% of all that exists in the universe in terms of mass energy. This means it must be around us all right now, a pervasive, invisible presence that permeates every corner of space, even the seemingly empty vacuum within our own solar system. It pushes on us gently, subtly, yet continuously, just as it pushes on every other galaxy, every star, every planet, every particle. Slowly but surely, with an accelerating, unyielding force, it forces all things apart, ever so gradually increasing the distances between cosmic structures, dictating the ultimate cosmic ballet, and setting the stage for the universe's long-term fate. Our gentle journey through the cosmic tapestry now brings us to the grandest instrument of all, the one designed to cast the widest net into the cosmic ocean and capture the most profound whispers of dark energy. We have come to understand that this mysterious force, while invisible, leaves its indelible mark on the universe by accelerating its expansion, subtly stretching the very fabric of space. To truly understand this influence over vast stretches of time and cosmic distance, a more expansive view is needed, a view that can encompass billions of years and billions of galaxies. This is precisely why, as we observed, if you truly want to spot dark energy's hand over time and space, you need to go big. And it's for that monumental purpose that the European Space Agency ESA has brought to life its magnificent creation, the Euclid Space Telescope. Imagine, if you will, that the universe is a sprawling ancient library filled with countless books, each a galaxy, each a star, each a particle. For centuries, we could only read a few pages at a time, or perhaps focus intently on a single illuminated manuscript. But to understand the grand narrative, the sweeping plot twists, and the overarching themes of this cosmic library, we need to be able to scan entire sections, to read millions of books simultaneously, and to see how their stories intertwine and evolve over vast periods. This is what Euclid is designed to do. It is not merely a telescope in the traditional sense. It is a dedicated cosmic cartographer, a celestial surveyor engineered to map the universe with a precision and scope previously unimaginable. Euclid is built as a wide-angle telescope, a design choice of profound significance. Unlike many telescopes that focus on narrow, deep fields to study individual objects with extreme detail, Euclid is designed to take in vast swathes of the sky in a single glance. This wide field of view allows it to survey an enormous portion of the cosmos with remarkable efficiency. Imagine trying to map an entire continent, not by meticulously drawing each blade of grass, but by taking aerial photographs of vast landscapes at once. This efficiency is critical for Euclid's mission, which aims to cover a significant portion of the entire celestial sphere. At the very heart of Euclid lies its incredibly powerful eyes, a sophisticated suite of instruments, including a 600-megapixel camera. This isn't just any camera. It's a marvel of engineering designed to capture light across a broad spectrum, specifically both visible light and infrared radiation. This dual capability is absolutely crucial for Euclid's grand cosmic timeline. Visible light, the kind our eyes perceive, is excellent for observing closer, brighter galaxies, giving us crisp, detailed views of the more recent universe. However, as light from incredibly distant galaxies journeys across billions of light-years through the expanding cosmos, its wavelengths get stretched much like a rubber band pulled taut. This stretching shifts the light from the visible spectrum into the infrared spectrum, a phenomenon known as redshift. By being able to detect infrared radiation, Euclid can effectively peer further back in time, capturing the faint ancient light from these highly redshifted primordial galaxies as they were billions of years ago when the universe was much younger and very different. This allows Euclid to create a seamless, continuous timeline of cosmic evolution from the universe's early infancy to its present state. Euclid's ambitious mission aims to survey an immense cosmic canvas covering over a third of the sky. To grasp the sheer scale of this endeavor, imagine painting a detailed mural that spans more than a third of the Earth's entire surface, but with enough precision to depict every single building, every tree, every tiny detail. That is the ambition of Euclid, and it will achieve this with a level of detail and sharpness that is 4 times greater than previously achieved by ground-based telescopes. While ground-based telescopes are powerful, their views are always subtly blurred and distorted by Earth's turbulent atmosphere, much like trying to see clearly through rippling water. Euclid, operating in the pristine, unblemished vacuum of space at its distant L2 point, is free from these atmospheric disturbances. This allows it to achieve unparalleled clarity and angular resolution, enabling it to precisely measure the subtle shapes, positions, and gravitational lensing distortions of billions of distant galaxies, providing the exquisitely sharp data needed for its scientific goals. The central goal of Euclid's mission is not just to take pretty pictures, though it will undoubtedly produce many breathtaking ones. Its core objective is to meticulously map everything going back 10 billion years. This means observing galaxies as they were when the universe was only about a quarter of its current age, providing an unprecedented multidimensional snapshot of cosmic structure throughout most of the universe's evolutionary history. By charting the precise positions, distances, and subtle distortions of these billions of galaxies across this immense cosmic timeline, it will be possible to create a revolutionary 3D map of the influence of dark energy. This isn't just a flat star chart. It's a deep volumetric representation of the cosmos, showing where galaxies reside, and crucially, how their distribution has evolved and how their shapes have been subtly stretched and distorted by the combined effects of intervening dark matter and the accelerating expansion of space itself. This intricate 3D map will provide an unparalleled window into the most pressing question surrounding dark energy, how dark energy's influence has changed or remained constant over all that time. This is the critical piece of information that will help scientists differentiate between the leading theoretical models of dark energy. If dark energy is truly an unchanging inherent property of space, like Einstein's cosmological constant, then its influence should be consistent and uniform throughout cosmic history. However, if it is a dynamic field like quintessence, whose strength can evolve and vary, then Euclid's precise data might reveal subtle variations in its power or its equation of state over billions of years. Euclid is perfectly poised to provide the definitive data needed to test these profound hypotheses, potentially confirming one of the existing theories, or perhaps even more excitingly, revealing something entirely new and unexpected that forces a complete rethinking of our fundamental physics. While Euclid will also look at individual stars, too, particularly in nearby galaxies, both to calibrate its sensitive instruments and to refine its measurements, its main objective is sheer volume. It is fundamentally a survey mission designed to gather statistical data from an enormous number of galaxies. This statistical approach is absolutely crucial because the effects of dark energy are often subtle on individual objects. You wouldn't notice its tiny push on a single star or even a single galaxy, but its cumulative pervasive influence becomes overwhelmingly apparent when looking at the collective behavior and distribution of billions of galaxies across vast cosmic scales. By analyzing these immense data sets, scientists can discern subtle patterns, tiny anomalies and grand trends that would be utterly invisible if they focused only on individual objects. This way, the subtle, pervasive pattern of dark energy will hopefully emerge, revealing its true nature through its cumulative effects on the largest structures in the universe. Much like a grand, intricate mosaic reveals its full picture only when viewed from a distance. The sheer statistical power of Euclid's data, its ability to analyze such a colossal number of cosmic objects, will be its greatest asset in this quest. The Euclid mission represents a monumental leap in our ability to probe the cosmic dark to illuminate the unseen. It launched on the 1st of July 2023, a date that will undoubtedly be remembered as a pivotal moment in humanity's quest for cosmic understanding. Since its launch, it has gracefully and precisely arrived at its designated L2 Lagrange point. A Lagrange point, as we've briefly touched upon, is a special gravitationally stable location in space where the gravitational forces of two large celestial bodies, in this case, the Sun and Earth, balance each other out. This allows a spacecraft to hover in a remarkably stable position with minimal fuel expenditure, much like a boat finding a perfectly calm eddy in a turbulent river. Specifically, the L2 point, located about 1.12 million kilometers, nearly a million miles beyond Earth, away from the Sun, is an ideal celestial sanctuary for space telescopes. It provides an incredibly stable, profoundly cold, and utterly dark environment, completely free from the interference of Earth's scattered light, its radiating heat, and the blurring distortions of its atmosphere. This allows Euclid to observe the distant universe with unparalleled clarity and sensitivity, capturing photons that have traveled for billions of years without any terrestrial interference. Euclid has already started taking its first breathtaking images, providing tantalizing glimpses of its future capabilities and the profound beauty it will unveil. However, these early photos of distant starscapes and swirling galaxies are primarily tests and do not yet represent the full levels of fidelity and the scientific precision that Euclid will be able to manage once it has finished its meticulous tuning and calibration process. Imagine a master craftsman meticulously tuning a complex orchestral instrument, note by note, until every string, every key, every component is perfectly aligned. A sophisticated space telescope with its intricate mirrors, detectors, and calibration systems requires similar precise adjustments before it can truly perform its full resonant cosmic symphony. Once the calibration process is complete, however, Euclid will embark on its ambitious 6-year mission to meticulously map out our stars and, more importantly, to hopefully answer important questions like what is the nature of dark energy and whether our understanding of the laws of gravity is really complete. It is a mission steeped in profound hope, a testament to humanity's unyielding drive to comprehend the universe that cradles us and to decipher the silent whispers of its deepest, most fundamental mysteries. So with bated breath and fingers crossed, we await the revelations that this magnificent mission may bring, hoping it can shed some much-needed light on the enduring mystery that is dark energy. For now, though, this enigmatic force remains largely shrouded in enigma, a cosmic shadow that shapes our ultimate destiny. It's only because of the universe's accelerating expansion, its relentless outward push, that we are aware of dark energy at all. It is otherwise utterly undetectable through any direct means we currently possess. We cannot bottle it, measure it in a lab, or even pinpoint its exact location. Yet despite its elusive nature, its impact is undeniable and overwhelmingly dominant. As we've discussed, it makes up over 60% of all that exists in the universe in terms of mass energy. This means it must be around us all right now, a pervasive, invisible presence that permeates every corner of space, even the seemingly empty vacuum within our own solar system, though its effects are too subtle to be felt on our small gravitationally bound scales. It pushes on us gently, subtly, yet continuously, just as it pushes on every other galaxy, every star, every planet, every particle. Slowly but surely, with an accelerating, unyielding force, it forces all things apart, ever so gradually increasing the distances between cosmic structures, dictating the ultimate cosmic ballet, and setting the stage for the universe's long-term fate, the existence of dark energy, and the subsequent launch of missions like Euclid. Underscore a profound truth about science. It is a continuous journey of discovery, a relentless pursuit of truth that often leads us to confront the limits of our current understanding. The universe, in its boundless generosity, continues to present us with puzzles that inspire awe and drive us to explore the very edges of possibility. Euclid, with its wide-angle gaze and its patient mapping, is our latest, grandest attempt to listen to the universe's deepest whispers, to understand the silent force that governs its ultimate destiny. The answers it unveils, or the new questions it reveals, will undoubtedly shape the future of cosmology for generations to come, enriching our understanding of our place within this vast and mysterious cosmic story. Our quiet voyage through the cosmos, illuminated by the gentle glow of scientific inquiry, has brought us to the doorstep of the universe's ultimate fate, a destiny profoundly shaped by the very mystery we've been contemplating, dark energy. For now, this enigmatic force remains an unresolved enigma, a cosmic shadow that dictates the grand ballet of galaxies. It's only because of the universe's accelerating expansion, that relentless, ever-quickening outward push, that we are even aware of dark energy at all. Otherwise, it would be utterly undetectable by any direct means we currently possess. We cannot bottle it in a laboratory, measure its precise composition, or even pinpoint its exact location. Yet its presence is undeniable, its influence overwhelming. As we've explored, despite its elusive nature, dark energy's impact on the universe is both monumental and dominant. It makes up over 60% of all that exists in the universe in terms of mass energy. Imagine trying to understand a vast, intricate play where the lead actor, the one driving all the action, remains perpetually hidden behind a curtain, only revealing their presence through the dramatic changes on stage. That hidden actor is dark energy. This means it must be around us all right now, a pervasive, invisible presence that permeates every corner of space, even the seemingly empty vacuum within our own solar system. It doesn't interact with light or ordinary matter in any way we understand, yet its power is immense. It pushes on us gently, subtly, yet continuously, just as it pushes on every other galaxy, every star, every planet, every particle. Slowly but surely, with an accelerating, unyielding force, it forces all things apart, ever so gradually increasing the distances between cosmic structures, dictating the ultimate cosmic ballet, and setting the stage for the universe's long-term fate. This relentless outward push, driven by dark energy, paints a particular picture of the universe's distant future, a picture that is both awe-inspiring and tinged with a profound cosmic loneliness. If the acceleration continues indefinitely, as current observations strongly suggest, then distant galaxies will eventually be pushed so far away and recede so rapidly that their light will no longer be able to reach us. Imagine them as ships sailing away on a vast, ever-stretching ocean. As they cross the horizon, they simply vanish from our sight. Similarly, distant galaxies will effectively be carried beyond our cosmic horizon, disappearing from our view forever, their ancient light stretched beyond detectability. In this scenario, our observable universe would gradually shrink. Over unimaginable eons, the light from all galaxies beyond our local group, a small cluster, including the Milky Way and Andromeda, would become so redshifted, so stretched by the expanding space, that they would fade into an eternal infrared oblivion, forever hidden from our sight. This vision often referred to as the Big Freeze, or more dramatically, the Big Rip, depending on the precise behavior of dark energy contrasts sharply with earlier cosmological predictions. For decades, many scientists considered the possibility of a big crunch where gravity would eventually triumph over expansion, pulling everything back into a hot, dense singularity, essentially reversing the Big Bang. But the discovery of accelerating expansion driven by dark energy has largely cast doubt on the Big Crunch painting. Instead, a much colder, darker, and more solitary picture of a universe destined for an ever-increasing expanse of empty space. One day, far in the unimaginably distant future, perhaps the only galaxy we will be able to see is our own, the Milky Way, standing as an isolated island in a sea of ever-increasing darkness. All other galaxies, those countless swirling beacons of light, will have been pushed out past the limits of detectable light, carried beyond the reach of any future telescope, however powerful. And then, in that profoundly isolated cosmic epoch, there truly will be only a single galaxy in the universe, at least as far as we can see, as far as any light can reach us. It's a humbling, almost melancholic thought to consider a future where the vibrant, crowded cosmic tapestry we admire today dissolves into an immense barren void, save for our own solitary home. At that unimaginably distant point, future beings, perhaps our descendants if life endures, might look up at a sky devoid of other galaxies. They may wonder where all the other galaxies have gone if they ever existed at all. They might question whether the universe eternally expands, or whether at some point dark energy will run out its mysterious wellspring of cosmic propulsion, finally depleting. The answer to this is one of the profound open questions of cosmology. Does dark energy have a finite lifespan, or is it a truly eternal, unchanging property of space? If by some grand cosmic turn, dark energy were to run out or somehow weaken significantly, the balance of cosmic forces would shift dramatically. At that point, the immense pervasive pull of gravity, the attractive force of all the remaining matter and dark matter, would finally dominate. With no opposing repulsive force, gravity would begin to draw everything back together, slowing the expansion, eventually reversing it. The galaxies would start to fall back towards each other. The universe would begin to contract, growing hotter and denser, leading inevitably to a scenario known as the Big Crunch. In this dramatic conclusion, everything would compress back in upon itself, collapsing into a hot, dense state, reminiscent of the universe's earliest moments, perhaps even a singularity, marking a cyclical end to cosmic history. But this remains a speculative path, a counterpoint to the more favored Big Freeze scenario suggested by current observations. So what is dark energy? For now, this remains the ultimate tantalizing question. The universe continues to hold its secrets close, revealing them slowly and often in riddles. Only time and possibly a space telescope called Euclid may tell. Euclid, with its wide-angle gaze and its meticulous mapping of billions of galaxies across cosmic time, is humanity's most ambitious attempt to read these subtle cosmic clues. It is designed to reveal whether dark energy is truly constant, an unchanging property of space itself, or if it is a dynamic evolving field that might one day fade or even reverse its cosmic push. The data it collects will be meticulously analyzed, every faint galaxy, every subtle distortion of light, every precise measurement contributing to a deeper understanding of this profound mystery. The journey we have embarked upon tonight, a gentle drift through the grandest ideas of cosmology, reminds us of the inherent humility required in the pursuit of knowledge. We might build the most sophisticated telescopes, devise the most elegant equations, and gather the most precise data. But the universe retains its deepest secrets, revealing them only when it is ready, and often only partially. Dark energy stands as a monumental testament to this truth, an invisible, undetectable, yet omnipresent influence that makes up the overwhelming majority of our cosmic reality. Its presence is inferred, its effects are observed, but its true nature remains shrouded in a profound veil of mystery. It is a force that is quietly, relentlessly shaping the ultimate destiny of all things, pushing galaxies further and further apart, dictating the very future of the cosmos itself. And perhaps in this very mystery lies the greatest wonder. The universe is not a solved puzzle, a completed book. It is a living, breathing, evolving entity full of surprises and hidden depths. The fact that so much of it remains unknown is not a flaw. It is an invitation to continuous wonder, to endless exploration, to the boundless stretch of human curiosity. The very existence of dark energy forces us to question our assumptions, to expand our conceptual horizons, and to imagine possibilities far grander and stranger than we ever conceived. It encourages us to keep looking up, to keep asking, and to keep dreaming of the answers that lie just beyond our current reach. This gentle contemplation of dark energy and the universe's ultimate fate is a reminder that we are part of a story far vaster and more intricate than any we could invent. We are stardust born from a cosmic beginning, and we are observers on a journey towards a cosmic destiny shaped by unseen forces. The profound questions about dark energy, what it is, where it comes from, and what its final act will be, are not just for scientists. They are for all of us, for anyone who gazes up at the night sky and feels a sense of awe and wonder. As you drift off to sleep, let the vastness of this mystery wash over you, not as a source of anxiety, but as a lullaby of boundless possibility, a gentle reminder that the universe, in its infinite wisdom, still holds secrets waiting to be unveiled. And perhaps in the quietude of your dreams, your own mind will begin to wander through the cosmic dark, seeking to understand the whispers of that unseen force.